I would say good morning, but I think it's closer to good afternoon now. So, hello, my name is Amir Neal.
And my name is Arturo Juan. And what we did in lab was working with microfluidic devices and see the applications that it has with fuel technology. And our mentor is Naran Kanajani.
Well, as we know, renewables are the future. It almost seems as though everywhere you look, you can find some sort of renewable energy that is powering something, whether it be your houses, your cars, your devices. So solar energy, hydro energy, wind energy, they have a presence in our everyday life. But we're not going to be focusing on that. We're going to be focusing on energy production through plants, specifically algae cells. So this is currently what our energy supply looks like. As you can see, there's a bunch of our energy production through non-renewables. And that's unfortunate because they're non-renewable. And we need to be placing more of an emphasis on renewable energies. If you look at the renewable energy sensitive pie here, you can see that opens up to other forms of renewable energy. And there's a great emphasis placed on biomass. So what we're going to do is use innovative approaches to microfluidics to increase this number.
As mentioned, we'll be using algae cells for our test specimen. Algae cells are a great source of biomass because they have lipids, and lipids are a high source of energy needed to make the biofuel. And to test these, to test the algae cells, we're using our microfluidic device to test different cultures of cells that vary in concentration, and they also vary in the environment in which they were grown. High lipid concentration can vary between cold water, salt water, or cold water, warm water, fresh water, or salt water. So we just wanted to test different cultures to see which better to mass produce in the future, so we can get that high efficiency in biofuels. This is a basic example of what our microfluidic device looks like. We have 3 inlet, or a microfluidic device to begin with. It's just a device that uses very small samples, about less than a millimeter usually, of milliliter. We have 3 inlets, and we have an outlet. They all meet at a center junction. The center inlet is where we drop our test algae cells, and the 2 outer inlets are where we have a separate medium, such as water, that's unreactive with our algae cells. When they meet at the center junction, the 2 outer inlets give the algae that's passing through a force through fluid dynamics. It pushes the algae cells in a center stream, flowing towards the outlet. And at the outlet, we have a vacuum attached. The vacuum just gives it an extra pull so that when the algae cells cross, they won't create a blockage. And to test, and so that the blockage won't prevent the readings that we'll be using with the laser. The laser that we'll be using performs Raman spectroscopy, and the spectroscopy gives you the data in which the lipid concentration of that specimen. The channels are extremely small. They're 50 micrometers in width, which is half the diameter or half the width of the human hair. This is a close-up of the junction of the microfluidic device. As you can see, we have a laser towards the exiting of the algae cells towards the outlet, and while the algae cells are exiting the junction. And you can kind of tell that you have that streamlined flow that the water adds to the cells. And we want to, as you can tell, we don't want we need the vacuum so that it doesn't create any blockages, so that we can just get a constant flow of algae cells.
Okay, so this is a cross-sectional view of our fabrication. The blue portion here is actually our microfluidics device, and it's made out of polydimethyl siloxane, otherwise known as PDMS, and that comes in like 2 containers, one in which a form that's really viscous, and then the other liquid is a little less viscous, and you mix it together and you cast it on top of this silicone mold here that contains the etchings that was previously shown, the 50 micron channels. Once you cure the PDMS on top of this mold and then vacuum out those air bubbles, you can then peel off the PDMS device off of the silicone mold, and it has to be done very carefully. And then we prepared a couple of glass slides and then treated it with ozone to remove any particles. We sandwiched our PDMS device between these two glass slides, and then to allow access for the inlets and the outlets, we drill these holes within the glass.
This is what our devices actually look like after we fabricated them in the lab. As you can tell, we have the two inlets right here, the two outer inlets, and then this is the center inlet. The example that I showed previous was just a simplified version of it. And they meet at a junction towards right there, and then the outlet is just located right above it. So they travel through the channels. We use pipette tips as the tubing because we don't really need such a high quantity of liquid. And we sealed them with epoxy glue around the pipette tips so that no gas leaks into the device or no fluid leaks out while we're testing it.
Allow me to give you some context on what this picture looks like. This is actually a close-up of the junction at which the three inlets meet. And what you're about to see, this is actually a very small video. And in the center channel here, you're going to witness a few polystyrene beads that sort of mimic algae cells because they are similar in size and weight. And by doing so, you can sort of get an estimate or an idea of how algae cells would actually react in the center channel. So I'm going to go ahead and play this little video. So just keep your eyes on those polystyrene beads. As you can see, they sort of accelerate past the junction because of the pressure of the cyclones. But another way to characterize these beads was to come up with a rate, a bead per minute rate, using two different devices. The first device, Microfluidic device, had 3 times as long channels as the second device. And as you can see, the associated rates with these different devices varies, obviously. The longer channels, the reason why the rate is lower than the rate of the second device is because the fluid stays in contact with the sides of the channel longer, and the resistance force that is exerted from the side channels slows down the fluid, so the longer channels have a slower rate associated with it. And during the last day of our lab, our mentor sort of wanted to broaden our minds a little bit. So to characterize cells and molecules better, he wanted to inform us about a way to analyze and characterize these cells and molecules using or by analyzing a naturally occurring phenomenon known as diffusion. If you look in the center of the slide here, you'll notice this fluorescent chemical that is rhodamine, and you'll notice that it starts to lose focus here. It's more focused along the junction here, and then it starts to just become very big. That phenomenon is known as diffusion. So using a couple of diffusion constant equations here, we're able to input the lateral height of diffusion and the time associated with it to come up with the diffusion constant. And then from there, we input the diffusion constant into the second diffusion equation that has been conveniently manipulated in terms of the radius of the molecule, and come up with basically an average radius for this molecule, which the specific chemical was rhodamine. So the molecule radius was 0.56 nanometers, which is about a fourth of the width of a DNA strand. So it's very, 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 very tiny. And this was just basically a way to understand where we could head in the future with perhaps other forms of energy.
Just a general overview of what we learned throughout the entire week. The microfluidic devices help us provide a more efficient method of the studying and making of biofuels, since we're at a time when we are desperate for these new sources of energy.
Microfluidic devices also aid in estimating the size of shells and even particles that are at the molecular level.
We'd like to thank our mentor, Veronica and Johnny, who couldn't make it today. But he was extremely helpful throughout the lab, and he was very patient with us. Our resident advisors, of course, for leading us along the way throughout this entire process. Dr. Carl Meinhardt from the Department of Chemical Engineering, who let us use his lab for this experiment. And of course, Jack and Cooke, program directors, because without them, we probably wouldn't be presenting you this information today.